In this lecture, we look at the chain rule and what it tells us about complementary trig functions. We're going to demonstrate the power of the chain rule by looking at some trig functions and write things in terms of the complement. In trigonometry, the complement of an angle theta is pi over 2 minus theta, or 90 degrees minus theta. It's the angle which completes the right triangle. In a right triangle, we will have an acute angle theta, and at the opposite corner is pi over 2 minus theta. Those two angles are complementary. If f of theta is a trig function of theta, then the trig function complementary to f, which I might write as co-f, is defined to be the complementary function of f is f of the complementary angle, f of 90 degrees minus theta, or f of pi over 2 minus theta. For example, cosine is the sine of the complementary angle. Cotangent is the tangent of the complementary angle, and cosecant is the secant of the complementary angle. Of course, with these complementary functions, we give them a name without hyphens. Cosine is written this way, cotangent written this way, and cosecant this way. This explains the use of the word co in the trig functions. Cosine, cotangent, cosecant are the sine, tangent, and secant of the complementary angles. The chain rule then allows us to write the derivative of a cofunction in terms of the original function. If g of x is f of the complement, in other words, if g is the complementary function, then we can use the chain rule and the fact that the derivative of pi over 2 minus theta with respect to theta, my variable here is theta, is minus 1. So the derivative of pi over 2 minus theta is minus 1. So if I take the derivative of g, I'm going to get the derivative of f evaluated at this complementary angle times minus 1. In other words, I'm going to get the negative of the derivative of the complementary function. In short form, the derivative of the complement of f is the negative of the complement of the derivative. We'll do some examples. Let's assume that we just know the derivatives of sine, tangent, and secant. We can use this result to find the derivatives of the remaining three cofunctions. If my function is the complement of the sine, then its derivative is the negative of the complement of the cosine. But the complement of the cosine is sine, so the derivative is negative sine. If my function is the cotangent, which is the complement of the tangent, since we know that the derivative of tangent is secant squared, then the derivative of cotangent should be the negative of cosecant squared. If my function is cosecant, that's the complement of the secant, then since we know the derivative of secant is secant tangent, then the derivative of cosecant should be negative of the complementary function, which is the same as negative cosecant cotangent. I see that I left an x out after secant, but we're looking at the negative of the complement of tangent x secant x. And that is the same as minus cosecant x cotangent x. We can display this with a table. Here are the 6 trig functions. The functions sine, tangent, and secant are on the left side of this table, and their complementary functions are on the right. So on the left side we have sine, tangent, secant, and on the right side we have cosine, cotangent, cosecant. Let's write out the derivatives. The derivatives of sine, tangent, and secant I'm going to put in the left column in red, and the derivatives of the cofunctions will be on the right. So for example, the derivative of sine is cosine, so the derivative of cosine is minus sine. The derivative of tangent is secant squared, so the derivative of cotangent is minus cosecant squared. The derivative of secant is secant tangent. The derivative of cosecant is minus cosecant cotangent. Here are my trig functions, and I'm going to start taking derivatives. If the derivative of sine is cosine, the derivative of cosine is minus sine. If the derivative of tangent is secant squared, the derivative of cotangent is minus cosecant squared, and so on. Later we'll see that this complementary function viewpoint simplifies computations of derivatives and eventually antiderivatives.